All right, guys, can you guys hear me? Can you guys hear me? All right, let's give it one more minute while we're receiving more attendance. Okay, today is the first lecture of our new session. We might have some new students, they might have some technical issues here and there. So as a common practice, we'll leave it maybe 1 or 2 more minutes. Okay, and also please do me a favor, please help to change your name into your registration name, because we might have some new students. Everyone use their fancy names, fancy avatar. So please do me a favor, change your name into a registration name, so I will be able to know who is who. All right. Yeah, and also like student asked me a question regarding the camera. So there's no obligation. You can try to turn on your camera, you can turn it off. It totally is up to you. So there's no obligation. If you think it's more comfortable to turn it on, you want to have more interactions, just do it. Otherwise, if you want to protect your privacy, feel free to turn it off. Okay. Our lecture has a lot of interactions. I'll be asking you guys to do a lot of questions back and forth. At least make sure you have a functional microphone. So as long as I ask a question, you can reply me. Or alternatively, I'm always have the chat channel on. So you can basically, turn on the chat channel and make sure you can, privately chat with me or answer the questions in the chat channel. So there's another way to have the interaction. All right. So long story short, interaction is very important. Whatever channels that works for you, either using the audio, or you can type with me, privately chat with me, or you can do a public chat. It doesn't matter. So this is a learning process, so no one will be judging you. All right? All right, I think we can get started. It's already 7:02. So welcome to our session 8, number theory session. All right, so let's go to our session, number theory. All right, so talking about number theory, I think this is actually a very important topic, right? A lot of students, they want to go to the American or Canadian math competition. They find a lot of challenge, a lot of problems in learning the number theory or solving the number theory related problems. Part of the reason is because in our regular lecture, we do not really offer, let's say if you go to our day school, you never offer a very systematic introduction about all the concepts about the number theory. We might learn something here and there, pretty much from our elementary school, but you never got a chance that let's sit down together, try to basically consolidate everything into a more well-organized lecture. So that being said, I think it is something very important that we need to have a lecture together, teaching you guys the most important concepts in the number theory, the most important, the classical problems in the number theory, and most importantly, the strategies, the solving strategies about the number theory. And this is actually where we come from. Fish and fishing, right? We like to give you guys more strategies, more common sense, the fishing technologies, rather than only the fishes. All right, so before we get started, let's have a very kind of like overview of why we have to learn the number theory, why number theory is considered to be like so important for our entire, not only math competition, but overall from a mathematics perspective. So we know that number theory is actually a very old topic. It's not something we just invented recently. It has been there for like, I think more than thousands of years. In the ancient Greek, the old Greek mathematicians, they're actually talking about the number theory, Pythagorean, so on and so forth. They're trying to figure out how the number works. Do we have some theories for all the numbers? Our famous mathematician Gauss actually has a saying. Gauss is very famous, right? So we actually have a saying that mathematician, or we say like the mathematics, mathematics is the queen of science, and number theory is the queen of mathematics. So that being said, you can see number theory is actually so important for the entire mathematics. So actually Chinese people add another saying that what is called the Goldbach Conjecture is actually the biggest pro in the crown. So just trying to say, number theory and some specific conjectures are like so important for this entire mathematics. So when we're trying to talk about the number theory, I think there are a few glory names, shining names we need to remember, because we're going to be seeing a lot of theories are actually either invented or introduced or like proved by those famous mathematicians. The first one is the famous Euclid. You shouldn't be unfamiliar with Euclid, right? We actually use, our Waterloo math competition, grade 12, is actually named after this famous mathematician. Euclid actually was born, I think, 300 before the century. Okay, he actually found out a lot of very important properties for number theory. For instance, he actually proved the prime numbers. We know we have the prime number, we have the composite number A. There are infinitely many prime numbers. So this is actually proved by Euclid using a very brief but very smart way. He also introduced the fundamental theory of algebra, and then he tried to prove that for any positive integers, the factorization is always unique. If you give me a prime number, I want to do a factorization. If you give me a composite number, I want to do a factorization. The factorization is always unique. You can't have like two different factorizations regarding the same number. So these are actually some very important properties from number theory, and they are considered to be the foundation of all the number theory related discussions. So the first one I want to talk about is Euclid. The second one we might keep talking about is actually Fermat. Fermat is actually a very famous mathematician. So he actually contributed two very important theorems for the number theory. One is what we call the Fermat little principle. This is something we're going to talk about in our current session. Fermat little principle. And the other one is the famous Fermat's last principle, or the last theorem. Okay, actually, the Fermat little principle is a lot more straightforward, and Euclid and Euler, they both actually, have some discussion for this. Especially Euler, he actually gave the proof in the year 1636. Okay. However, Fermat's last principle is actually mysterious there for a long time. So people really have no idea how to prove it. So you know what? At the very beginning, Fermat mentioned he has already found out the solution, the proof, but because of the very limited space, he won't be able to give the entire proof for this Fermat last principle. And actually, no one have no idea, Fermat does have a proof or not, or will he just like say it? But actually, the mathematicians spent centuries trying to find out what is the real proof for the Fermat last principle. Actually, I think there is a English mathematician, Andrew Wiles. He actually gave the proof in the year 1995. So basically, from the time that Fermat gives this last principle all the way to we prove it, we spent almost like 300 years. So you can imagine how complicated this last principle is. And Fermat, sometimes people just believe he just do not ever have a solution. He's just trying to, brag there, give some information, kind of like a misleading. All right, another very important person we want to talk about is actually Euler. We're going to talk about Euler. We're going to learn some principles raised by Euler in our session as well. Euler actually, basically, the first contribution is, like we said here, he actually proved the Fermat little principle in the year 1636, Fermat little principle. And also, he actually gives a lot of definition for our Diophantine equation, so on and so forth. So actually, he also put a lot of contribution for our number theory. Especially for this Euler guy, I have to say, he's considered to be a time traveler. So why? Because if you check his resume is like so crazy. He actually got his undergraduate degree at the years 15. 15 years old, he already got his undergraduate degree, which is incredible. And 19 years old, he got his PhD degree of mathematician. And also In the years of 20, he already become the Academy of the Russian Academy of Science. This is totally incredible. 20 years old, he just became the Academy of the Russian Academy of Science. And he actually contributed a lot of very important stuff for the mathematician, for like the entire mathematics, not only for the number theory. For instance, he actually invented the sign fx. You know, fx is actually for the functions, right? He actually invented something like sine, cosine, tangent. You know, all these kind of symbols were actually invented by Euler at his younger age. And he actually got blind. You know, his left eye got blind in the year of 28. And in the year of 59, he got totally blind, 2 eyes, totally blind. And also at the year of 76, when he was actually in the middle of doing something, he just stand up and saying, I'm gonna die. And then right away he fell off and died. So I have to say for Euler, this person is actually kind of like his entire life. He is a genius for sure. And his entire life is full of this colorful, interesting, mysterious legends. And he did a lot of significant contribution for the entire, not only number theory, but also the entire mathematics. And the last name we want to talk about is actually the famous Goldbach, right? The famous Goldbach conjecture. Even though today we have no people really find out the correct solution, the accurate proof for the Goldbach conjecture. Right? Our famous Chinese mathematician Chen Jingrun actually did a significant work for this proving process for Goldbach conjecture, but still he's not 100% there. So Goldbach, what we say is like 1 + 1, and Chen Jingrun actually go to 1 + 2. It's very close, just like one step forward, and we'll be able to find out the accurate proof for this Goldbach conjecture. So actually, you know, this is actually, you can see there's a lot of glory names, shining names for the entire number theories. Most of these famous mathematicians, you heard about the names in your elementary school, your high school, whatsoever, they did a significant contribution for the number theory. So again, that being said, what should I say? The number theory is actually something so important. And most of the mathematicians, they like to contribute for this entire topic. And that's the reason why we like to, you know what, put some emphasis on the session and try to basically present you guys the most important concepts for the number theory. All right, this is kind of like a warm talk, kind of like a warm up. What we're going to talk about this number theory and why number theory is like so important. So moving forward, before we get started and jump to our today's lecture, this is like a lecture's outline, our syllabus. What will we be talking about in our today's session? So in this session, we're going to talk about the following concepts. We're going to get started talking about the divisibility and some important properties of divisibility. So this is, I think, something quite important and quite straightforward because we know about how to do a division, what is the divisibility, pretty much from our elementary school. And then moving forward, we're going to talk about the prime numbers and composite numbers. These are considered to be the two most important two types of number for the number theory. And most of our discussion is going to be focused on either prime numbers or the composite numbers. We're going to talk about the greatest common divisor, least common multiple. This is a concept you learn from your elementary school, right? And now we're going to find out more flowery properties about these two very important concepts. We're going to talk about the modular arithmetic. So trust me, modular arithmetic is considered to be the foundation of this entire number theory. A lot of like flowery properties or important concepts that are all elaborated from the modular arithmetic. And that's the reason we like to focus about, put a lot of emphasis about this arithmetic, modular arithmetic. And then moving forward, we're going to talk about three very important number theory properties. Three very important number theory properties. You're going to see that for our Canadian and American math competition from time to time. AKA, they are the format, little principle. Like I said, this one was actually proved by Euler about 400 years ago. The other one is Euler's torsion formula and our famous Chinese remainder theory. So these theorems are going to help you do a lot of interesting number theory related problems you can see from the Canadian and American math competition. And we're going to focus on some very detailed explanation and application of those theorems. Moving forward, we're going to talk about some advanced number theory theorems. They're not super important, but you know what? Sometimes if you know some advanced theorems, that's going to help you to expedite the solution process, and you can get your answer faster. And then we're going to talk about some number base. You know, we're so familiar about this decimal, right? And people are also familiar with this binary, right? Using 2 as the base, especially if you want to do more about computer science. The entire computer world was actually built up using the binary theorem. But actually you have like more, right? Not only 10s as the base, not only 2s as the base, you know the hex, right? You can maybe use 3, 4, 5, 6. You can use whatever number as the base. We're going to try to give some of kind of the very important properties, how to do conversion between different bases, and what are the most important concepts for different bases. We're going to talk about some factor-related theorems, factorization, and try to find out the factor is actually one of the key components we're trying to do for this entire number theory part. We're going to give you some very interesting properties you can utilize to expedite your solution process. And if we have some time, we're going to talk about some Diophantine equations and their properties. Diophantine equations may be not very familiar if you see the name. However, whenever we go to the concept, I give an example, you'll find out, okay, this is what I know from our high school or elementary school. But we just want to take this opportunity to give you guys some flowery properties of how this Diophantine equation works. Right? So this is kind of like a big overall what we will be talking about, right? Before we get started, I think it is very reasonable that we have a forecast, what we will be learning for our entire lecture. All right, if all good, let's jump to our first part, our lecture number 1. Let's try to talk about the divisibility and its most important properties. Okay. And also, by the way, if you have any questions, let me know. You can always interrupting me by using either audio, right? Or you can type from the group chat, so I'll be able to see you, right? Try to have the interaction. It's very, very important. All right, let's go to our lecture number 1. Let's try to talk about something about the divisibility. So divisibility is actually something we learned from our elementary school, right? So how does this divisibility can be defined, right? What is the definition of divisibility? We can do it something fairly quick, something like this. An integer b is divisible by an integer a. Of course, a cannot be 0, right? So we can write a type b if there is an integer x such that b equals to a times x, right? This is pretty much an elementary school thing. B can be written as b is an integer, a and x, they're all integer. B equals to a times x, then I'll be able to say, okay, b is divisible by integer a. And we use such a sign, a type b, try to present a is actually a divisor of b, or b is divisible by a, right? So that being said, we can call b a with a little pipe. We can either say b is divisible by a, or we can say a is a divisor of b, right? This is actually the definition how the divisibility works. Two numbers, which one is divisible by the other guy, or the other guy is a divisor of which guy. So this is something what you learn from your elementary school. There's nothing flowery, there's nothing to say. That's it. All right, as long as we know about the definition, let's try to talk about some important properties of divisibility. So trust me, most of them are like super easy, and you learn that from your elementary school. So the first one is, let's check it out one by one. If we have like, let me change the color to red. If we have m, n, and d, they're all integers, okay? then we have the following statement hold. N is the divisor of n. Of course, any number is divisible by itself. Nothing to say. If D is a divisor of n, well, n is a divisor of m. So that being said, you see, n is here, then all the way D must be a divisor of m. Of course, this is what we say the transitivity. Or we can say we can pass on this property, right? A is the divisor of B, B is the divisor of C, C is the divisor of D, so all the way A is the divisor of D. This divisibility properties can be passed on to different numbers, which is totally understandable. Number 3, if D is a divisor of n, D is a divisor of m. Okay, so therefore D must be a divisor of A times m plus B times m, provided A and B, they're both integers. So trust me, this is actually a very important property for the divisibility. What we call it is a linear property. It means that, let's say, A is a divisor of B, A is a divisor of C, so therefore, any kind of linear combination about B and C, B times X plus C times Y, right? All of them can be divisible by using A. This is also quite understandable, right? So 2 parts, you do any kind of linear combination, you'll be able to generate a new number. This is a new number, right? So this newly generated number from B, from C, must be divisible by the original A, right? Quite understandable. But trust me, this is an extremely important property, even though it's like so easy, but our American, Canadian math competition, they always use it. So having good understanding, just try to imprint it into our head. This is going to be something so important. Okay, let's continue. If D is a divisor of n, then I multiply the same integer on 2 sides of this kind of D and n, you will have exactly the same thing, right? AD is also a divisor of AN. If you times something on the 2 sides, the entire property will still hold. Okay, now this is kind of like a multiplication, right? We're times something, but can we do a division? Can we divide something on the 2 sides? Yes. If AD is a divisor of AN, A is the same, A is not a 0 for sure, then you will be able to cancel A on the 2 sides, having D is a divisor of N, which is quite understandable, right? One is a divisor for everything, right? One is actually, everyone can divide 1, right? So nothing to say. What if I have n as a divisor of 1? N is an integer, n is divisor of 1, aka there are not too many options for n, right? N must be either equals to +1 or -1. Quite understandable, right? If you have a divisor of 1, this divisor must be either equal to 1 or -1. D is a divisor of 0. We defined everything divides 0. Because in the divisibility, we barely talk about something about 0, right? 0 is not exactly what we want to say. So we just basically have a definition. We define everything divides by 0. It's only a definition. You don't want to see that too much. You don't want to use it too much. It's only a definition for the sake of being harmonic. If n is a divisor of, if a 0 is a divisor of n, because normally speaking, we do not want a divisor to be 0, right? We always say A is a divisor of B. Of course, A cannot be equal to 0. But if you really want to ask me, what is n is divisible by 0 or 0 is divisor of n, then we can define n equals to 0. So 0 divides only 0. This is only a definition. Again, there's nothing too flowery. People just try to be more harmonic for this entire system. We just define that. And also, if D and N, they're positive, and D is a divisor of N, then of course, D will be lesser or equal to N, right? I give you a number. This number's divisor should be smaller or at least the same value as the original number, right? You can't have a divisor which is bigger than the original number, right? I think these properties are like so easy. There's no need to have like so many complicated stuff, right? We just basically try to understand how it works. Okay, the student got a question. Can you repeat number 3, please? Of course. Number 3 is here. This is very important. It says D is a divisor of n. D is a divisor of m. Then D must be divisor of any linear combinations between m and n. I'll give you an example. Sometimes an example can really help you out. Number 3, right? Okay, I'll give you an example. 3 is a divisor of 6, right? 3 is a divisor of 9. So that being said, 3 must be a divisor of any linear combination between 6 and 9. So let's say x equals to -1, y equals to +1. Then 3 is a divisor of -6 plus 9, which is 3, of course, right? Let's say x equals to 2, y equals, I don't know, maybe 9. So 3 will be divisor of 12 plus 81. 3 will be divisor of 93, which makes sense. So that being said, as long as you have such a relationship, 3 or A is a divisor of something, A is a divisor of another thing. So these two guys, any kind of combination, linear combination, must be also divisible by using the original number. Right? I think this is something understandable, right? So you have like some numbers and then you do some combination. That's actually how it works. Yeah, any question, just let me know. I'm actually monitoring the group chat all the time. Just let me know. Don't be shy. So any question is a good time for you to sort it out. All right, so these are considered to be a very kind of like a elementary school property, right? Nothing too complicated. And in order to go to the North American math competition, I think there are 2 more things you need to remember, which is also quite understandable. So the other one, this is like number 10, or say number 11. The other one is, let's say, given n, a, they're both integer, then n must be divisible by a plus 1, a plus 2, all the way a plus n. N must be divisor of a plus 1, a plus 2, all the way to a plus n. What does it mean? This is like a mathematical language, right? If I translate into a human language, so that being said means what? A times 1, a plus 1 times a times a plus 2, all the way a plus n. This is actually the product of n consecutive integers, right? N must be a divisor of the product of n consecutive integers. I give an example. Let's say 3 must be divisor of 19 times 21 times 20 times 21. 5 must be a divisor of 20, 21, 22, 23, 24, right? So n must be a divisor of the product of n consecutive integers. Okay, this is actually it's very easy peasy property, right? You can actually do a quick imagination. You can find out how to prove it. Okay, this is actually number 11. And actually, you know what? Number 11 can do one step forward. Not only n is a divisor of the product of n consecutive integers, but also, let's say, n, a, they're both integer, right? Exactly the same concept. Actually, n factorial is exactly the same thing. Not only n is a divisor of the product of n consecutive numbers, but also n factorial. N factorial is also the divisor of the product of n consecutive numbers. So that being said, not only 3 is here, 3 factorial can be written as this. It's a divisor of 19, 20, 21. Not only 5 is a divisor of this, 5 factorial is also 20, 21, 22, 23, 24. You see? So number 11 and number 12, these two properties are actually connected, right? Number 11 is considered to be like an easier version, and number 12 is considered to be a more advanced version. Okay, I think this is quite understandable, right? This is not something too complicated. You can give some numbers, you can find out the proving process, just like a couple of lines. Try to remember it, because from time to time, you know, AMC or Canadian exam might use it from time to time. All right, I think these are basically the most foundational, the basic properties about the divisibility. I think you guys already know pretty much every one of them, right? Maybe one or two have some quick tweak, but the majority are something quite understandable. All right, so after we know all those concepts, before we jump to the problem, I want to give you guys some strategies. So normally speaking, when you're dealing with some divisibility related problems, what are the common strategies? So that's actually the second part of our lecture. We're going to talk about common strategies. Okay, our lectures are always contained by 3 parts. Number 1, let's talk about some basic definition, theorems, concepts. Number 2, let's go for some common strategies. And number 3, let's use the common strategies to solve some real problems. So these are like the 3 steps, how we learn a new concept, how we put them into a real application. Okay, what are the common strategies when you're dealing with the divisibility related problems? Normally speaking, in North American math competition, you need to know 3 common strategies. Number 1, factorization. Factorization. As long as you're dealing with the number divisibility related problem, factorization is always important. Let's say I want to give you m as a divisor of n. So your first reaction before you do everything is just try to do a prime factorization for m. Try to do a prime factorization for this. Let's say this is maybe prime 1, prime 2, all the way prime k, right? This may be prime 1, prime 2, all the way to prime m. So before you do all those kind of analysis, try to do a factorization about the divisors, about arranging the numbers is always important, and that's going to help you to open kind of like the initial phase of doing the divisibility, if not the entire number theory related problems. Okay, so factorization. You know what? Actually, this entire number theory lecture, in our 10 lectures, I'm going to be very long-winded. I'm going to keep talking about factorization, because they are so important. They're considered to be our step number 1 before you do all those kind of number theory problems. Okay, number 1, factorization. Number 2, when you're dealing with the divisibility related problem, there are always a certain type of number you want to put some attention. That is prime number. Prime number is always special when you're dealing with the divisibility related problem. Okay, I'll give you an example. Let's say I give you a number. I say 3 is a divisor of m squared. 3 is a divisor of m squared. Then automatically, I can say 3 is also a divisor of m. Is it right? If 3 is a divisor of m squared, then I can say 3 must be a divisor of m. Why? Because 3 is a prime number, right? So basically, either the 3 must come in from 1m. It is impossible that, let's say you have 2 parts, m times m, then some of the m contribute something to 3, some of the m contribute something to 3, right? It is impossible because prime number, there's no way to decompose it, right? You can only factorize 3 into either 1 and itself. So that being said, as long as you see 3 as a divisor of m squared, then you can be very safe to say actually 3 is a divisor of m, right? So that being said, a prime number as the divisor can be a little bit different. Then what about I say 7 is a divisor of m cubic? Okay, then I can also directly say, you know what? If 7 is a divisor of m cubic, then 7 must be divisor of m, right? Again, because 7 is actually a prime number. So there's no way for you to decompose 7, right? 7 must come from directly one m. It is impossible. Some m's, they work together to generate all the factors of 7. So that being said, you see, you can directly simplify your problem, even though at the very beginning, 7 is a divisor of m cubed. But now you can directly say, actually, 7 is divisor of m, which is quite understandable, right? Okay, the only reason I can do such a simplification is because my 3, my 7, they're both prime numbers, right? Prime numbers to be the divisor can be always a little bit special. That's going to help you to solve the problem or help you to simplify the problem a little bit. However, trust me, this property, you can't really say this is work for all the numbers. For instance, I give an example. Let's say I say 12 is a divisor of 6 squared, right? Then you can never say 12 is a divisor of 6. Is it right? This is hell no. Right? 12 is a divisor of 6 squared does not necessarily mean 12 is a divisor of 6. Why? Because 12 is a composite number, right? Only the prime number can have this kind of luxury and you can do the simplification here and there. But prime numbers like this does not necessarily mean composite number can do the same thing. Okay? So a student got a question. So for 7, if 7 is a divisor of m cubed, would 7 also be a divisor of m squared, m fourths? What do you think? Of course, yes. That's a perfect question. If 7, let me try to see from here. If 7 is a divisor of m cubed, automatically 7 is divisor of m. If 7 is divisor of m, 7 must be a divisor of m to the power of k. K can be 1, 2, 3, 4, 5, whatever, right? So that's a very good question. As long as you see 7, which is a prime number, be the divisor, there's a lot of simplification process, right? You do not really have to do a lot of calculation or something. You can simplify your problem right away because prime number is like so unique. However, this property does not necessarily work for the composite numbers. If composite number is the divisor, you really can't say too much, right? Why? Because prime number is so unique, not only for the divisibility, but also for this entire number theory. A lot of interesting, if not flowery properties, they're only working for prime numbers. No composite numbers have such beautiful property. And the good part is in our math competition, most of the time, if we want to give you some problems, I want to challenge you, most of the time, we're talking about the prime numbers. Okay, we're talking about the prime numbers. Okay, this is the second strategy. As long as you're dealing with the divisibility related problem, try to pay attention for the prime numbers because the prime number can always give you something a little bit different, some flowery properties. All right? Number 3, the third common strategy is exactly what we talk about in our property number 3. If A is a divisor of m, A is a divisor of n, then automatically A must be a divisor of the combination of m and n. Of course, x, y, they're also integers, right? So this one, trust me, this one like so easy, so understandable, but our American, our Canadian math competition is really testing it from time to time. So having a good understanding, especially the application, how to use such a property can be extremely important. No worries, in today's lecture, we're going to give you different kinds of problems, try to help you guys basically exercise and practice how you can use such a property. And the last but not least is for our divisibility related problem, and if not for this entire number theory related problem, most of the time, we just talk about the positive integers. Positive integers. So unless the question give you specify specifically, right? Most of the time they give you some A, B, C, D, or some X, Y, whatever. Most of the time they're talking about positive integers. That's going to make our life a little bit straightforward. You don't have to think about the negative part because the positive, the negative, the sign doesn't make any difference, right? It's only this kind of like our divisibility related property is going to make a difference how we're going to do all the problems. All right, I think that's pretty much the second part I want to say, the common strategies, 4 very important strategies. Factorization, pay attention to the prime numbers, and then try to use the linear combination property, and also just focus on the positive integers. These are the big directions, the 4 big directions for our number theory related problems. Okay, these are the methodologies. If all good, let's go to our section number 3. Okay, let's try to use the technology, right? Those kind of methodologies, try to have a look at it. What are the classical problems for our North American math competition when we're talking about the number theory part? So classical problems. Okay, so let's go to some real problems. Let's go to our question number 1. Question number 1 is an easy, we'll say, warm up question. Okay, we won't directly jump to the most complicated one. Let's do some easy one. Help you guys do some quick warm up. This problem goes like this. Given A, B, N, they belong to positive integers. Like I said, right? Most of the time, we just talk about the positive integers. For any given K also belongs to the positive integer, we have B minus K is a divisor of A minus K to the power of N. And then the question asks you to prove B minus K must be a divisor of A minus B to the power of N. Okay. So I have A, B, N, 3 numbers. They're all positive integers. I can see that for any given K belongs to a positive integer, B minus K must be a divisor of A minus K to the power of N. Okay? This is actually given by the problem. With this information in hand, the question asks you to prove B minus K must be also a divisor of A minus B to the power of N. Okay, so whenever we see a problem, what is the thinking process, right? This is extremely important. We want to talk about from day 1. So as long as you see a problem, of course, the problem is going to give you a bunch of condition, bunch of information, so on and so forth. And also at the end of the day, the question asks you to prove some conclusion for sure. So normally I want you guys to know this is, let's change the color to here. Let's say this is actually something you need to prove, right? Of course, if you want to prove something, this is something you do not know, right? You need to prove it. And this is given by the problem. As long as this is an information given by the problem, this is something you know, right? You have something you know, you have something you do not know. So there's a gap. There's a gap between what you know and what you do not know. So the most important thing is you need to bridge the gap, right? Find out what's the gap between the 2 parts. All right. How can I bridge the gap? I think the most important thing is you need to find out the relationship right? If there's no relationship between these two expressions, of course, there's no way for you to solve the problem. So how can you find out the relationship? Of course, based on the observation. So if I do a quick observation for whatever I know and whatever I do not know, of course, I can find out the left-hand side, they're exactly the same, which is good, b minus k, right? But the right-hand side, one is a minus k to the power of n. One is a minus b to the power of n. All right. So the most important thing looks like I need to find out the relationship between the first one and the second one, especially focus on the right-hand side, right? How can I find out the relation? If I find a proper relationship between the two, so hopefully I'll be able to solve the problem in no time. So our common sense is just try to find out the relationship. Find the relationship between 1 and 2, right? This is a common sense, right? So how can I find out relationship? I just have to list them out. Let's say a minus b to the power of n. This is what I have to prove, right? This is number 2. What's the relationship between a minus b to the power of n, which is what we call number 2, and number 1, a minus k to the power of n. How can I find out relationship? As long as I talk about a relationship, there must be adding some things, subtract something, so on and so forth, right? There are 2 expressions. You need to put them together. You need to do some kind of manipulation. So this part is, I think this part is not something crazy, right? You do a subtraction, b to the power of n, k to the power of n, right? Now you find out the relationship. Okay, you find out the relationship. Okay, so it looks like the question tells you that b minus k, if I use the color maybe white, blue, b minus k is a divisor of this guy, a minus k to the power of n. And the question asks you to prove b minus k is a divisor of a minus b to the power of n. So intuitively, what should you do? Who can tell me? Intuitively, what should you do? I have a simple green expression which contains 2, which contains 1, and also a new part, right? This new part is actually what I generated using my manipulation, so on and so forth. The question already tells you here. This is what you know. I use a check, right? And then the question asks you to do this. I use a question mark. Then you intuitively, what should I do? I'm going to ask maybe Michael, what should I do? Michael Mao, excuse me. Michael Mao, yes. You can unmute yourself if you want to talk.
Okay. You can do prove the b to the n minus k to n is divisible by b minus k.
Is it right? So I want to show, right? B minus k is also divisible by b to the power of n minus k to the power of n. Why? Because as long as I prove that, if I prove b minus k is a divisor of the red part, I already know b minus k is a divisor of the yellow part. Then using what? A is a divisor of m, A is a divisor of n, so therefore A must be a divisor of any combination between m and n, right? Because you can take this as m, you can take this as n, the combination m minus n, automatically this is going to be a divisor, this is going to be divisible by b minus k. Is that right? This is a very intuitive thinking process, right? Question number 1, I don't want to give you something too complicated, but try to use some easy problem. You can identify the thinking process. This is number 1 is what you know. Number 2 is what you do not know. right? If I can basically using number 3, right? I can prove b minus k is a divisor of number 3. That being said, my b minus k is a divisor of number 2. My b minus k is a divisor of number 3. So therefore, b minus k must be a divisor of, oops, sorry, this is number 1, right? Sorry. I find out b minus k is the divisor of number 1. B minus k is divisor of number 3. Then automatically, b minus 3 must be divisor of any combination between the expression 1 and the expression 3, aka that's going to be your expression number 3, right? This is an easy problem, but you can see the thinking process. So that being said means what? I just want to show b minus k as a divisor of b to the power of k, b to the power of n minus k to the power of n. Is it something conspicuous, or this is something very crazy? Who can tell me? Is this something very easy peasy, or not something so easy? Who can tell me? Are you guys familiar with such an expression? B minus k minus b to the power of kn minus k to the power of n. Can this guy easily be divisible by using b minus k? Do you guys notice? This is actually a very famous factorization. Like I said, factorization is something so important for our entire, not only divisibility, but also number theory. So b to the power of n minus k to the power of n, this is a very important divisibility. I mean, this is a very important factorization you need to remember. How this guy can be factorized? This guy actually equals to b minus k, b to the power of n minus 1, b to the power of n minus 2k, all the way b k to the power of n minus 2, k to the power of n minus 1. Okay, this is a standard factorization for b to the power of n minus k to the power of n using our binomial theorem, right? Because binomial theorem is not in the scope of our current lecture. It's more like for continuum probabilities. Normally speaking, our sessions are segregated. So we're not going to use too much for the other sessions, but we just happen to say this, right? So b to the power of n minus k to the power of n, this is a very important common factorization you guys need to remember. Okay, this is actually derived from the binomial theorem. All right, as long as you see this, I think this is very conspicuous, right? Because b minus k happen to be here, of course. Or we say, obviously, b minus k as a divisor, b to the power of n minus k to the power of n, aka you prove this. As long as you prove this, just try to use this, right? Any combination between number 1 and number 3 will be able to generate number 2, and that's going to be divisible by b minus k. So we can just basically say that obviously b minus k will be a divisor of this minus this, and this is exactly a to the power of n QED. You see, that's it. So like I said, this is like a warm-up question, right? We're not talking something too crazy, but this warm-up question actually give you guys some very important, kind of like a little heads up, right? What are you going to do for the number theory related proving problem? So at the very, very beginning, you need to find out the relationship, something you know and something you do not know, right? Find out this is what you know, this is what you do not know, and this is the relationship. Okay, find out the relationship is our step number 1. Step number 2 is using our famous property, right? A is a divisor of n, A is a divisor of n, then any linear combination between the two will also be divisible by A, right? And then our step number 3 is actually using what? Some factorization. Put all the little pieces together, you get what you need. You see, it looks like every single problem is actually a combination of our different strategies together, and you get what you need. So far, so good? That's our warm-up question. Question number 1. Okay, any question, just let me know. So, we want to have a more dynamic lecture, right? Any question, let me know. I'm here to help you guys out. Okay, this is our number 1. If all good, let's go to our question number 2. Our question number 2, let's go for one problem that comes from 1989 AIME problem. Okay. We'll try to give you some problem from the American, from Canadian, from some international math competition. Just give you guys some ideas. Look, actually, different problems, they're using exactly the same strategy. So let's have a look at it. This is an old AIME problem. I think these days, it's pretty much in the AMC 12 territory, talking about complexity. So what we say for such a problem. So this problem says, if A is lesser than B, lesser than C, lesser than D, lesser than E, they are consecutive positive integers. Okay, so as long as you read, I think you need to highlight the most important words, consecutive positive integers. They're not like random, they're consecutive. Okay, such that B plus C plus D is a perfect square. Okay, A, B, C, D, E, adding everything together is a perfect cube. With all those information, the question asks you, what is the smallest possible value of C? Okay. I think number 1 stuff is, as long as we read a problem, I need to convert the human language into this is our human language, right? Into our mathematical language, right? Human language is more like some English wording. Our mathematical language is using expressions, right? That's going to be something easier. And then let's try to find out whatever we know, whatever we do not know, so on and so forth. So question basically give us like 3 conditions. Number 1 is these 5 guys are consecutive. Number 2, I add these 3 is perfect square. I add these 5 is perfect cube. So let's have a look at it. B plus C plus D, this guy equals to a perfect square. Okay, I'm just going to put it here. A plus B plus C plus D plus E equals to a perfect cube. Okay, perfect cube. And then with all those information, the question asked me to determine the value for C. Okay, so this is whatever I know, right? This is what I know. This is what I do not know. Again, I want to find out a relationship. Again, if there's no relationship, there's no way for me to solve the problem. And what is the relationship? Let's try to think about it. B plus C plus D, they give me a perfect square. A, B, C, D, E together, they give me a perfect cube. Perfect square, perfect cube. Let me try to use a kind of like a number to denote perfect square and perfect cube, because I don't know them, right? Maybe perfect square goes like this. Perfect cube goes like this. Okay, is it okay? Just try to make my life a little bit easier. So now I have B plus C plus D equals to M squared. A, B, C, D, E equals to N cubed. And then the question asked me to prove was the minimum value of C. Okay, if you want to find out the relationship or the value for the C, of course you want to find out how C looks like, right? How this kind of like C looks like. But you have like B and D here. Now you have A, B, D, E here. These are not C's. Is it something kind of like, easy or something that I have to do to convert everything into C? Because the question really asked me to do C. The question never asked me to do B, E, D, A or something like that, right? So can we do some quick tweak to make sure we can only deal with C rather than deal with other numbers? Who can tell me? Because the question asked me to do C, but I have B, D, A, E. These are not C's, right? I can't do too much for the right-hand side for now, right? These are N's. These are basically what is given by the problem. But at least can I do some kind of quick tweak to get rid of the numbers I do not like, but only leaving the numbers that I have to deal with, aka C. I'm gonna ask maybe Hansen, what can I do?
Let A equals C minus 2, B equals C minus 1, D equals C plus 1, E equals C plus 2 to the direct consecutive. And then so B plus C plus D is just 3C equals to M squared. And then A plus B plus C plus D plus E equals to 5C equals to NQ.
Is that right? I think that's a brilliant idea because the question only asked me to deal with C. I don't have to waste my time about A, B, D, like whatever. And the question also mentioned A, B, C, D, E, they're what? They're consecutive numbers. So therefore, using the basic arithmetic, right? This is our kind of arithmetic sequence, right? The basic arithmetic sequence property, B plus C plus D just happen to equals to 3C. And this guy just happened to equals to 5C, which makes sense, right? So therefore, that's a very important step forward. I get rid of whatever I do not need, but I only retain C, which is what I need. 3C equals to M squared. 5C equals to N cubed. Okay, now it looks like I need to determine the number for C, and then basically using these two expressions. Okay, let's go to the first one first. 3C equals to M squared. 3C equals to M squared. Okay. 3C equals to M squared. I think you have like 3 and C, two numbers on the left-hand side, and you have M squared on the right-hand side. So automatically, you can say that, okay, 3 must be a divisor of M squared, right? C must also be a divisor of M squared, which makes sense, right? Two things, multiply them together. Of course, these are the divisor of M squared. Well, if you can recall what I just mentioned, as long as you're dealing with divisibility, you need to pay attention about the prime numbers, right? Because prime numbers can always help you do a little bit simplification. 3 is a divisor of M squared. 3 is a prime number, right? So automatically, 3 is a divisor of M, right? C is a divisor of M squared, but I don't know C is positive, C is composite or is prime, I have no idea. So I can't see. So I can't say C is a divisor of M, right? So I can't do too much about non-prime numbers, right? But I'm pretty sure I can do something for the prime numbers. So 3 is a divisor of M squared, aka 3 is a divisor of M. If 3 is a divisor of M, so my M, I can write M equals to 3K, right? 3 is a divisor of M, so M must be multiple of 3. So that being said, I'm going to put it back. I'm going to put it back into the original expression. 3C equals to M squared, 3K squared, 9K squared. So therefore, C equals to 3K squared, right? Why I'm doing this? The question asked me to determine the value for C. So maybe I have to do some simplification. At least I see 3. C is actually in the form of 3K squared. right? This is exactly using what we introduced. Always focus on the prime number related stuff. Okay, as long as you do one, I think you can do exactly the same thing for the second, right? These are really kind of like very mechanical. You do one, you do the same thing for the second. The second will be, let's try to do this together. So I'll change the color maybe to black. 5c must be a divisor of 3. I mean, like 5c equals, put it here, equals to n cubed. So therefore, either 5 is a divisor of n cubed, or c is a divisor of n cubed. Again, I can't say too much about this part because I don't know C is composite or prime, but at least I know 5 is a prime number. So that one says 5 must be divisor of n. If 5 is a divisor of n, I can let n equals to 5k, right? Exactly the same thing. I'm going to put it back to this original expression. 5c equals to 5k cubic. So therefore, c equals to 25. Let's say, so this time maybe I'll not use k, I'll use l, okay? Try to do a little bit, kind of make some difference, because previously I used k, right? So that's going to be equals to c equals to 25l cubed. Now I have the second expression of c. Let's check it out. C can be written in the form 25l cubed. C can also be written in the form 3k squared. The question asked me to determine what is the minimum value of k of c, right? The question asked me to determine the minimum value of c. So that means that I just have to find out a number. Can either be written as 3k squared or can be written as 25l cubed, right? They must be, I mean, this must be like the same thing, right? Can be either. So I must find out the c can be written as 3k squared and also at the same time must be able to be written as 25l cubed, right? I need to find out such a value, and that's going to help me to find out the value for c, and I want that value as small as possible. So taking from there, I think this is going to be something kind of like easy and understandable. So now you're trying to find out, let's try to put here. You want to find out the values for c. Can be written as 3k squared, can also be written as 25l cubed at the same time, and you want to have the c as small as possible. So this one actually means what? This one actually means what? I need to find out the value for k and l, right? Let's try to find out some value for k for a while. I can basically fit into these two expressions. They're equal to each other, and I want a value of k and l as small as possible. So I think taking from here, there's nothing too complicated. I just have to do some enumeration. So who can tell me what kind of numbers I need to give for k, for l? I can make sure this expression holds, and also k and l, they're as small as possible. Because k and l as small as possible means c as small as possible. Who can tell me what is the value for k, for l? There's no trick here. You just have to play with the numbers, try to find out some numbers, right? And you'll be good to go. Of course, you want to try some small numbers, 1, 2, 3, 4, 5, right? You don't want to try 3,000, right? Who can tell me what are the tiny, tiny numbers? For k, for l, I can make it just as small as possible. I get answer right away. 30 seconds, think about it. No trick. You just have to do some quick trials and errors. Right? Either enumeration or trials and errors. Please tell me, what are the two numbers? This is not a magic, right? You should you should get a number fairly quick. Please, everyone, put your answers into the group chat. This is something easy, so I'll let you guys to figure it out. I'm gonna ask maybe Alex An.
You got L equals 3 and then K equals 15.
L equals to 3, K equals to 15, right? Yes, that's actually the correct answer. So basically 3 times 15 is x, 3 times 5 perfect square equals to 25 is 5 square times 3 cube. So that's it. There's nothing too flowery. So you just basically do some trials and errors and you get what you need. That's basically how you find out the value, right? So AKA, K equals to 15, L equals to 3. So that being said, what is the minimum value for C? C minimum will be 3 times K squared, which is 675. That's it. That's the value for C. You see, this is actually if you go a quick recap for this question, this is exactly using what we introduced in our lecture. At the very beginning, you want to do some quick manipulation. You want to find out what is the value for C. You want to find out what you know, what you do not know. But the moment you come to here, conditional react, right? You're going to find out either 3 is a divisor for m squared or C as a divisor for m squared. Like I said, as long as you're dealing with the like the prime numbers as a factor, you can do a quick simplification from square to m itself. Same technology applies here, right? As long as you see this, you'll be able to see this. And then you put them together, you just try to find out what is the minimum number that can basically fit such a relationship. So that part, there's no more tricks. You just have to basically sort out what is the minimum value, and that's it. You see, these are a very intuitive process, right? These technologies are so helpful. We're going to use them from time to time. All right, so far so good. So like I said, this problem is like kind of like an old AIME problem. These days, there should be roughly in the AMC 12 territory if we're talking about the complexity, but the entire process is very understandable. All right, if we're good, let's go to one a little bit more complicated, one step forward. Our problems are always designed in such a way you can do one step forward or one step forward. Let's go to another AIME problem. A relatively difficult, but still very understandable whenever I give you the answer. So this is a problem we're looking at that comes from 2001, AIME 2, question number 10. Okay, let's talk about this problem. Again, let's focus on the thinking process. How are we going to deal with such a problem, right? How do you think, which is extremely important. So this problem says, how many positive integer multiples of 1001? Okay, positive integers of 1001 that can be expressed in the form of 10 to the power of j minus 10 to the power of I, where j and I, they're integers, and you want to make sure I and j, I is lesser than j, and they're all between 0 all the way to 99. Okay, how many positive integer multiples of 1001 can be expressed in the form of 10 to the power of j minus 10 to the power of I, where I and j, they're actually integers taken from 0 all the way to 99. Okay, so it's kind of like a long story short. I want to find out something like this. At least I want to find out 1001 is a divisor of 10 to the power of j minus 10 to the power of I, right? 10 to the power of j minus 10 to the power of I. This guy looks like, how can I find out such a thing? My left-hand side is like 1000 plus 1, right? And my right-hand side is a kind of like a two power things doing a kind of a division together, right? Doing a like subtraction together. This is the only condition that I know. I want to find out different combinations for I and j to make it work. Okay, as long as you see such a problem, like I said, if you really have no idea, try to think of our common strategies. We talk about 3 or 4 most important common strategy. Like the fourth one is not so important. We said they're all positive integers. So generally speaking, the first 3 are very important. So the first one, factorization. Second one, using the combination about A is the divisor of B as the divisor of C. And our last one is try to pay attention for this prime number related factors, right? So I think for our first observation, this is quite understandable. I can do a factorization, right? Because j, 10 to the power of j, 10 to the power of I, is kind of like you can do a factorization, right? So that being said, 1001 is a divisor of I, 10 to the power of j minus I minus 1. Okay, so far, so good? Okay, if that's the case, let's have a quick observation. You have 1001 as a divisor of this guy times this guy. So obviously, 1001 can never be a divisor of 10 to the power of I, right? This is obviously, I'm going to put it here. Obviously, 1001 is not a divisor of 10 to the power of I, of course. This can't be a divisor, right? So that being said, if you want to make this equation holds, the only possible scenario is 1001 is a divisor of 10 to the power of j minus I minus 1. Does it make sense? I think that one makes sense, right? This one makes sense. Okay, but this guy, 10 to the power of I minus j, at the end of the day, this is going to be 10 to the power of k, right? Minus 1. So among those numbers, who can tell me which one can be divisible by 1001? So before we jump to the very generic analysis, let's give one example. Let's try to understand how the thing works. 1001, you wanted me to divisible by 10 to the power of k. Let's say I'll give you a name. This is k. To try to make my life easier, okay? Minus 1. Who can give me a very easy example? What kind of scenario I can make a k? What's the value for k to make sure I can find a value 10 to the power of k is a divisible by 10 to the power of 1, by 10,001. If you want to find something generic, you got to get started with something easy first, right? With something easy first. Somebody mentioned 0. Okay, perfect. K equals to 0. Your left-hand side is going to be 1001 divisible by 1 minus 1, which is 0, right? Which makes sense. However, if you go back to the original question tells you that I can't be equal to j. So therefore, forget about 0, right? I and j, they're not the same. You need to find me a non-zero one to make it work. Who can tell me what kind of number I can give to k to make sure 1001 is the divisor of 10 to the power of k minus 1? Trust me, this is a very important AMC trick. Even AMC 10 is going to test you something like this. Not to say AIME, not to say something complicated. Even AMC 10 will test you something like this. I'm going to ask maybe Oliver, what kind of K that works for this? You can give one example.
6.
6. Is it right? That's a perfect answer. But how can I think of 6? Yeah, of course you can do an observation, you can find out, right? But I'm going to tell you something very important. Try to remember this. This is going to be extremely helpful. This guy. Let's try to do some quick rearrangement. The left-hand side can be written 10 to the power of 3 plus 1, right? The right-hand side is 10 to the power of k minus 1. So, how to make sure it works? Intuitively, if you have 10 to the power of 6 minus 1, can be written as 10 to the power of 3 plus 1, 10 to the power of 3 minus 1, right? So intuitively, you see, this is actually one of the very important 10 to the power of 3 plus 1. So trust me, in the future, as long as you see something like this, try to convert it into 10 to the power of k or 10 to the power of m plus 1. And then you'll be able to see what you need. You know what? This time I tell you 1001, or next time if I tell you it was 999, 10 to the power of k minus 1 or plus 1, whatever, right? Try to do exactly the same thing. 999 will be 10 to the power of 3 minus 1. Again, k equals to 6. Is it right? This is a learning process. As long as you learn one, you should automatically know the other, right? You can't just basically, I only know one, right? So this is plus. Learning mathematics, you need to be very dynamic. 1001, you put it into 10 to the power of 3 plus 1. If one day I give you 999, go to 10 to the power of 3 minus 1, right? The logics are exactly the same. So that being said means what? Okay, now 10 to the power of 3 plus 1, right? I know equals to 10 to the power of 6 minus 1. This is like one example. J minus I minus 1, right? I give him one example. So that being said means what? 1001 as a divisible by 9999999. There are 6 9s, right? 6 9s. 1001 is divisible by 6 9s. But the question is not only asking for 6, right? The question is asking for 10 to the power of j minus 1. If the j minus 1 can be different digits, then how many scenarios you can also make sure 1001 can be divisible by that guy. So that being said, the original question asks you 1001 is divisible by 9999. There are how many 9s? J minus I 9s. Is that right? So this is what you know. After your hard calculation, you figure out, okay, 1001 is divisible by 6 9s. But the question says, if this is not only for 6 9s, it has j minus I 9s. What kind of makes this j minus I equal? You can make sure that 1001 is also divisible by j minus I different 9s. Is that right? Of course, I is lesser than j is lesser than from 0 to 99, right? If I choose random numbers from 0 all the way to 99, I can generate different kinds of 9s. Like the length can be j minus I different digits. Along all those digits, how many of them can also be divisible by 1001? Right? So how can I deal with that? This is what I not know, right? So the gap is very clear. I know whenever there are 6 nines divisible. But the question asks me, not only for 6 nines, how many nines, different nines, right? 6 or 7, 6, 7, 9, 10, all the way to 99 nines. How many of them I can make sure they're still divisible by 1001? And this is actually the most important thing for such a problem. Think about it. How can I find out the gap between the two? Basically, you know that whenever this guy equals to 6, it works, right? But the question I ask you is, besides 6, some other numbers, can you find some other fancy numbers? Also make sure it works. There must be some relationship between the 6, right? The 6 must be something important. It can't be just like a random number, right? There must be something I can utilize from 6. I can transfer into j minus I, and then voila, the entire thing works. But the most important thing for you is, how can I find out the relationship? What is the gap? Who can think about it? The gap must be very easy. There must be a strong relationship between 6 and this I minus j or j minus may, whatever you need to find out, right? But what is the relationship? You know what? As long as you get confused, I think we're all on the same page. We need to sort it out, right? As long as you figure out the relationship, my work is done. But how can I find out a relationship? If you get confused, if you get stuck, don't give up. Let's try some easy scenarios, right? Before you jump to something crazy, why don't you try something easy, right? Hopefully, you might find out a relationship. From the easy pattern, go to the complicated pattern, right? I'm not relying on you to guess out a solution right away, but there must be some strategy to help you guys to do something easy, find out a pattern, find out a relationship, and then kind of apply them into something difficult. So, 9, 6, too much. Let's go for something easy. What about I have something that's divisible by 2 nines, right? At the very beginning, there are 6 nines. It's too complicated. Let's go for 2 nines. I have a number divisible by 2 nines. Okay, if that one is, check, I have this number. Then this number can be divisible by 3 nines. This number can be divisible by 4 nines. This number can be divisible by 5 nines. Divisible by 6 nines, right? Intuitively, you need to ask you, this is like the thinking process, right? I'm actually showing you guys the thinking process. I'm not like reading the answer for you, right? How do you think whenever you do not know the answer? Who can tell me? If you follow my hint, if I know a number is divisible by 99, can you somehow figure out this number can be divisible by, I don't know, maybe 99, 3 nines, 99, 4 nines? Because like the entire problem is talking about how many nines, right? 5 nines, 6 nines? Maybe you can find out some pattern from there. 30 seconds, think about it. And please post your answers into the group chat. Please find out. If you have no idea what it is, why don't you just give a number, right? I think 30, let me find out the number. Maybe, I don't know, 33 is divisible by 99, right? Let's use the 33 to try the other numbers. Which one is divisible, which one's not divisible, and hopefully you'll find out a pattern from there. It's a trials and errors, right? No one knows the answer right away, but we can try to think about it, right? So I see a lot of students have some thought. Okay, let's ask some student, try to just, let's do like brainstorming, right? I'm gonna ask maybe Rachel Qi. So what do you think?
I got the multiples of that number.
Okay, multiples of that number. Okay, that's a good idea. Multiples of that number. Oh, of 99, right? Okay, perfect. Who else?
No, I mean like the multiples of the amount of nines.
Okay, like the multiples of the amount of 9. Okay.
Yeah, like 2 9s, 4 9s, 6 9s.
Perfect. 2 9s, right? In our case.
Yeah.
2 9s. Perfect. Okay. Yeah. I think this is something you know what? If you don't know what you're doing, why don't you try something, right? Of course, 33. I'm going to put 33 here. It's not divisible by 999, right? But 33 is divisible by 9999. So these are 2 9s. These are 4 9s. 33 is not divisible by 5 9s, but 33 is divisible by 6 9s. So that being said, means what? Means as long as you have the multiple of their original digits, right? Previously, it was like what? 2 digits. As long as you go to 4 digits, as long as you go for 6 digits, you will be able to retain this divisibility property, right? Like I said, you don't have to prove this, but this is quite conspicuous as long as you see this 1, 2, 3, 4, 5, right? So that being said means what? Okay, from here I find out a pattern. As long as I know something divisible by 2 9s, then I can say a multiple of 2 9s, 4 9s, 8 9s, or 6 9s, right? It will be divisible by the same number as well. This is a very conspicuous stuff you get from there, right? So that being said, as long as you have some easy example, then what you want to guess for such a thing? Who can tell me what I need to guess? What are the special ij minus i's I can make sure they're always divisible by 1001? Who can tell me? You need to learn from here, right? This quick example already give you that direction. Whenever you have 2 9s, a number is divisible by 2 9s. It must be divisible by 4 9s, 6 9s, 8 9s, 10 9s, whatever. Now, a number is divisible by 6 9s. Then it must be divisible by what?
So j minus I would be divisible by 6.
Is that right? This is very comparable, right? That's the reason why you want to do something like this. Exactly. As long as, I'm going to change the color here. As long as j minus I is a multiple of 6, I can make sure 1001 is divisible by 10 to the power of j minus I minus 1, right? So now it looks like what you need to do is that as long as you have I is lesser than j is lesser than 99, right? You want to find out all the numbers between this. Whenever you do a j minus I, you want to make sure this is a multiple of 6. You want to find out all those numbers to make sure they're the multiple, like all those numbers for j, for I, and make sure they are basically the difference as a multiple of 6, right? J minus I as a multiple of 6, our work is done. So now it actually becomes an easy number theory problem, right? I have a bunch of numbers I and j from 0 to 99. I want to pick up 2. I want to do division. Excuse me. I want to do a subtraction. I want to make sure the difference is actually a multiple of 6. How can I arrange all those numbers, right? I think that part you can actually do something very easy. So you have to do some casework. So how can I do the casework? What about my I and j? They're all 6 multiple. Two numbers, they're both 6 multiple, and then I do a division, and then I do a subtraction. The difference is always a 6 of multiple, right? So how many 6 multiple between 0 and 99? You have 0, 6, 12, 18, all the way to 36. There are 7 numbers there, right? You just close your eyes, randomly choose 2 numbers from the 7, and you make a difference. They're all good. C72. Right? So far so good? You choose 2 numbers from the 7. They're all 6 multiple. The difference is always 6 multiple. Voila. What about my I and j? They're all 6 multiple, then plus 1. Right? They're both 6 multiple plus 1. Then you do a subtraction. There will be 6 multiple. How many you have? 1, 7, 13, all the way 97. There are also 6. There are also, oh, sorry, there are 17, not 7. Not 7, excuse me, 17. From 0 to 99, there are 17 6 multiples, right? From 0 all the way to 99, there are 17 numbers that are divided by 6, remainder is 1, right? Exactly the same thing. Third one, there must be 6 multiple, then the remainder is 2. You have like 2 all the way to 98. Also, you have 17, C72. 4, this is a very mechanical, right? 6 multiple 3, 3 all the way to 99. Then you have like 17 as well, C72. And what about all those numbers are divided by 6, multiple is 4. This is 4 all the way to 94. This time, there are only 16 numbers. You can use your finger. You can count them one by one, right? So from 0 all the way to 99, you randomly pick up the number, divide 6, remainder is 4. There are only 16, not 17. But you're going to do the same thing. 6, C, 6, 16, choose 2. 6. What about you want to choose I and j? They are all divided by 6. The remainder is 5. 5 all the way to 95. They're also 16. Say 16, 2. So that means that how many numbers you can add them together to make sure I minus j is a multiple of 6? You just have to add everything together, right? That's going to be 4, C, 6, 17, 2, 2, 16, 2, 7, 84. Voila. That's the solution for such a problem. Yeah, it's AIME problem. It combines some number theory and also some counting and problem, like counting things, right? But generally speaking, I think the thinking process is fairly understandable, right? You see, this problem is nothing too tricky. We start from our factorization, and then we try to find out a pattern. This is something we're going to learn in this, right? As long as you're dealing with something difficult, why don't you try something, has more pattern, right? Some easy pattern. Hopefully you get the pattern from the easy problem, and taking from there, you can get what you need. So far, so good? This is like a AIME problem I just gave you guys. See, divisibility is actually the way how we basically find out from factorization, from combination, we get what we need. So far, so good? Perfect. If all good, let's go for another problem. Let's go for a Canadian problem, okay? Let's go for, we talk about some American problems. Let's talk about some Canadian problem. Let's go for one problem from Euclid. This is also a problem you're talking about, the divisibility. This is a problem from 2000. Euclid, question number 9. Okay, so we talk about this problem in our Euclid boot camp. Okay, so yeah, maybe we're gonna talk about it like a bit faster here. So what does this problem say is a permutation of integers 1, 2, 3, 4 of n is the least of all these numbers in some order. So of course, you guys already know permutation. For example, 3, 1, 2, 1, 2, 3, there are 2 different permutations of the integer 1, 2, 3. A permutation 1, 2, 3, a1 all the way to an of integers 1, 2, 3, all the way to n is said to be fantastic if a1 plus a2 all the way plus ak is divisible by k. This is the condition. For each k from 1 to n. What does it mean? Give an example. The question of just varied, you don't really understand this. So they give an example. 3, 1, 2 is a fantastic permutation because 3, 1, 2, if I basically list them out, if I only have a1 is divisible by 1, right? When I have a1 and a2 together, I add a1 and a2 together, this is divisible by 2. And then I add a1, a2, a3 together, this is going to be divisible by 3. You see, every time you add a new number, ak, the entire expression a1 all the way to ak will be divisible by ak. You need to place the number in a so smart way to make sure every time, whenever you add a new one, this is going to be divisible by ak. However, the question gives you a negative test case, like a negative case. 2, 1, 3 is not a fantastic permutation because a1, 2 is divisible by 1, no problem. But a1 plus a2, this is not divisible by 2. a1 plus a2 equals to 3, right? It's not divisible by 2. So that being said, not all the permutations are fantastic. Some of them are, some of them are not. With all those information, the question talking about, show that there's no fantastic permutation for n equals to 2000. It means that whenever I give you 1, 2, all the way to 2000, regardless, how you want to arrange such the 2000 numbers, there's no way for you to make sure a1 plus a2 all the way to ak is always divisible for k. And the second one is ask you, does a fantastic permutation exist for n equals to 2001 or not? Okay, because normally speaking, Euclid question number 1 is always easier. Question number 2 will be a little bit more difficult, right? If there's number 3, it will be a lot more difficult. So let's have a look at it. How are we going to deal with this? Let's go to the A part. 2000 numbers, putting them together. I want to say this is a fantastic permutation or not. You know what? Always at the very beginning is easier for me to put. Let's say if I only have a1, you put whatever number is divisible by 1, right? a1 plus a2, you just have to put 2 numbers, adding them together, divisible by 3, divisible by 2, right? And then a1 plus a2 plus a3, divisible by 3. It looks like the more you go to the later terms, the more constraint you have. You have to make sure the previous one all works, plus my one is working, right? The more you go to the very beginning is more flexible. So that being said, the most challenging one is a1 plus a2 all the way to a2000. Is it going to be divisible by 2000 or not, right? This is going to be the most constrained one. If that's the case, why don't I just get started with the last one? We're going to use some reverse engineering. Right? Like I said, the first couple of terms, you have too much flexibility. But the more you go to the later terms, the more constraints you're going to be having. So let's have a quick look at it. What's going to happen for the last one? Is it possible when I have my 2,000 terms, adding them together, this is going to be divisible by 2,000? 1 plus 2 plus 3 all the way to 2,000. Is it going to be divisible by 2,000? This is what? This is an arithmetic sequence, right? 1 plus 2,000 times 2,000 terms divided by 2, right? 2,000, is it okay or not? This is going to be what? 2,001 times 1,000. Is 2,000 divisible by 2,001 times 1,000? Of course not. So therefore, this is not going to happen. So that being said means I don't really care about the first couple of terms. You do whatever you like. But I can make sure as long as you go to the last one, this won't be divisible by 2,000. So therefore, there is no way to have a fantastic permutation for 1 all the way to 2,000. Easy peasy, right? Okay, let's go for the second one. Is it possible I have a fantastic permutation for n equals to 2001? 1, 2, all the way to 2001. Can I have a fantastic permutation? Again, same strategy, especially for Euclid. All the strategy you did for question number 1 will be totally applicable for question number 2. It will be totally applicable for question number 3. Again, exactly the same thing, right? I don't really care about the first couple of terms, but I always start with the last one because the more you go to the back, right, the more challenging you're going to be having. So have a look at it. 1 plus 2. So that's going to be my A1 plus A2 all the way to A2001, right? I want to say this is going to be divisible by 2001 or not. So that means I want to add everything. 1 plus 2 all the way 2001. That one equals to what? That one equals to 2001. That one will equals to 1 plus, excuse me. That one will be equals to 1 plus 2001 times 2001 divided by 2, right? That one will be 2001 times 1001. Of course, this one is divisible by 2001. 2001 times 1001 will be divisible by 2001. So that being said, if I add everything together, that's going to be a fantastic permutation. But I just can't give the conclusion this is working, right? I have to check every single term to make sure it works. Now I only checked for the 2001 terms, it works. But what about A1 plus A2 all the way to A2000? This is going to be divisible by 2000 or not, right? I have to check everything. I can't only check the all the terms, right? I have to check everything. But the problem is, how can I know my value for A1 all the way to A2000? Because this is a permutation. I don't know which one. A1 might be 1991. A2 might be 2, right? I don't know what it is. However, let's try to do a quick tweak. I have no idea how this guy looks like. But this guy actually equals to what? A1 plus A2 all the way to A2001 minus A2001. Yeah, somebody said, of course. Why are we? Of course. But no worry. Even though this is very conspicuous, but that's going to help you do something because you know how to determine all the values because there are 2001 values here, right? Regardless what you're going to do, you have add everything together, A1 all the way to A2001. That's going to be your 2001 times 1001, right? This is what you're going to do here. right? You want to make sure you can find out 2000 is divisible by 2001 times 1001 minus a 2001, right? You want to find out if this is possible or not. If you can happily find out any arrangement for that, at least you can secure this 2000 term. But how can I do that? This is, again, going to be using the very important linear combination. I said, A is the divisor of M, A is the divisor of N, A must be divisor of mx plus my. Why? Check it out. Here is 2000. I want to do a very quick tweak. I'm going to change this part into 2000 plus 1 times 1001 minus a 2001. Okay, is it doable? Of course. Do we have 2000 as a divisor of 2000 plus 1 times 1001 minus a 2001? Now that being said, means is it right? Okay, let's check it out. If 2000 is this guy times this guy, and 2000 is also a divisor of this guy, then automatically my 2000 must be a divisor of a 2001. Is it right? This is your M, this is an N. 2000 is a divisor of M plus N. 2000 is a divisor of M. 2000 is a divisor of M plus N minus M. Exactly. Is it right? This is exactly what I need here. Like I said, this is extremely important. It's like so easy, but you keep using them back and forth. American, Canadian, they all use it. Are we all on the same page? Are we all on the same page? Is it good? Can I have some feedbacks? Is it good? Right? So that being said, 2000 must be divisor of 1001 minus a 2001. Okay, student got a question? Yes? Yes, I see XML, Lee's. You wanna have, if you have any question, just let me know. Yeah, any questions, you can just let me know, okay? All right. So that being said, as long as I can figure out a value for a 2001, and I can make sure 2000 is a divisor of 1001 minus a 2001, my work is done. A 2001 must be chosen from 1, 2, all the way 2001, right? 2001. So can I find out such a value for a 2001 such that 2000 is a divisor of 1001 minus 2001? Yes. I think the only option you have is a 2001 equals to 1001. Is that right? 2000 is going to be a kind of like the divisor of 0, which makes sense, right? Okay, so it looks like as long as I can do such an arrangement, I can make sure 2000 will be a divisor of A1 plus A2 all the way to A2000. The condition is my A2001 must be equals to 1001. Okay, looks like it is also good, right? But can I just wrap it up? Okay, this is going to be a fantastic permutation. Of course I can't. I have to check every single one, right? To make sure it works. So my next one is, what about my 1999 is a divisor of A1 plus A2 all the way to 1999. Right? If I can do this, my work will be done. We're going to do exactly the same strategy. 1999 is a divisor of A1 plus A2 all the way to A2001, right? Minus A2001 minus A2000. That's the only way for me to work, right? I already know the total sum of A1 all the way to A2001. A2001, I just know this is 1001. I have to basically figure out a value for A2000. I'm going to be using the same strategy again and again and again to make sure if I can construct every single term. So let's check it out. What's going to happen over here? Again, this is 1001 times 2001, right? This is what we just introduced. This is 2001. This is A2000. 1999. Very mechanical, right? 1999 will be, this is going to be what? Yeah, this is 1001, excuse me, 1001, right? Because A2001 is 1001. 1001, right? So that's going to be what? 1000. I'm going to consolidate these two terms together. That's going to be 1001 times 2000, right? Minus A2000. Just do a quick combine the likely terms. Okay, what are we going to do? Exactly the same thing. I'm going to change this part into 1001 times 1999 plus 1 minus A2000, right? Divided by 1999. 1999 will be divisible by 1001 times 1999 plus 1001 minus A2000. Exactly the same strategy as we did for the previous one. Because you're telling me this guy is divisor by this entire expression. And also this guy for sure is divisible by the green part. So obviously 1999 must be divisible by 1001 minus A2000. Exactly the same strategy. Everything is exactly the same. Okay. Again, what's going to happen here? What's going to happen here? In order to make sure 1999 is divisible by 1001 minus A2000, the only possible way is A2000 equals to 1001, right? Because there's no other ways to make it work, right? A2000 can take from 1 all the way to 2001. But as long as you see this, wait a minute, you got a problem. Now you're telling me that A2000 must be equals to 1001 to make sure it works for 1999. But previously, you just told me that A2001 must also be equals to 1001 to make sure it works for 2000. But wait for a second. This is a permutation, right? Permutation from 1 all the way to 2001, you can't have two numbers are the same. You give 1 to 2001 equals to 1001, and then you give the same 1001 to A2000. You can't make two numbers are the same for the same permutation, right? So this is the contradiction. Right? In a permutation, every number must be different. You won't be able to have A2000 and A2001, they're the same number. Then of course, this is going to be a problem. Right? Okay, so that being said, if there's a contradiction, means what? Means, you know what? This is not going to happen. So these two problems, they're exactly the same thing. You won't be able to see a number for 2000 or number for 2001, they both work for this fantastic permutation. For this fantastic permutation. So far, so good. Can I have some feedbacks? All right. If all good, let's go for another problem, because this is our lecture number 1. We have to do some introduction, waiting for some students. So I'm going to do extra maybe 5 to 10 minutes, but normally speaking, we'll stop at 9 o'clock. So hopefully you guys can understand. Like first problem, we have some administrative stuff, so we might be a little bit slow, but normally speaking, we have 2 hours. If you're busy, you have to go, you're free to go, okay? Let's go for our last problem for today's lecture. I really like to give you different kinds of problems, help you guys to expand our horizon. Okay, let's go to our question number 5, right? So this is actually 1997 Ukrainian Math Olympiad practice question. Okay, so this is actually a very interesting problem. I like to show you guys. Try to prove. Regardless how many 3's are inserted between the 2 zeros in 12008, the result must be divisible by 19. Regardless how many 3's are inserted between the 2 zeros in 12008, the results must be always divisible by 19. What does it mean? It actually means that, let's say I have a number 12008, right? I want to insert a bunch of 3's into this, between these 2 zeros. Can be 1, 3, 2, 3, can be n 3's, right? Regardless how many 3's you inserted between these 2 zeros, the result is always divisible by 19. Okay, how can I do such a problem, right? It looks like a little bit fancy. I think the question per se is very understandable, right? I give you 12008. I want to insert some 3's just right between these 2 zeros. I want to say how many, regardless how many 3's I inserted, the answer is always divisible by 19. I think before we get started, before I talk about the solution, I think you need to ask yourself a very normal question. Why? Why they give you such a number, 12008? Why they want to say this is divisible by 19, right? Because all the math combination, all the numbers, they're specially designed. There's no number given for fun, right? Why they give 19, not 17, not 21? Why is 12008, not 12007? So I think this is a very intuitive question you want to ask for ourselves, right? Why they like to give you this? There must be some reasoning behind it. Okay, so again, like I said, I'm not reading you the answer. I'm trying to guide you guys the thinking process. As long as you get stuck, right? So maybe let's try to start with something easy, something understandable, right? So maybe you're not so easy to see how many 3's, regardless how many 3. Let's get started. What about there's 1 3? What about there are 2 3's? What about there are no threes, right? 0 threes, 4 threes, 5 threes. Let's have a quick look at it. Maybe, hopefully, I can find out some pattern and taking from there, I get what I need. Difficult problem, we always get started with this. Let's have a look at it. 1, 2, 0, 0, 8. Let's say there's no threes, 0 threes inserted. You find out this guy is actually 19 times 6, 32. Okay, this one is divisible by 19. What about I insert 1 3 in between? That guy is actually 6, 3, 3, 2. What about I insert 2 3s in between? This guy is going to be 9, 3, 3, 3, 2. Check it out. What a magic. If there's no 3, just like this. If you insert 1 3, you're kind of insert a 3 here. If you insert 2 3s, you kind of insert like 2 3s here. Okay, you see, this is a magic, right? Like I said, all the numbers, they're given for a reason. They're specially designed to make sure you can do it fairly quick. So that being said, it looks like what? It looks like I have a sequence. 1 2 0 0 8. 1 2 0 3 0 8. 1 2 0 3 3 0 8. All the way 1 2 0 3 3 3 3 3 0 8. This is n threes, right? I want you to prove every single term in this sequence is going to be divisible by 19. Do you guys follow me? This is an A1, maybe A0, for instance. This is A1. This is A2, because there's 1, there's 2, 1 3s, 2 3s, all the way n threes. This is AN, right? You want to make sure that, okay, every single term in this sequence is going to be divisible by 19. I, right? I is between what? I is actually between 1, 2, all the way to n. Is it right? Do you guys follow me? Can I have some feedbacks? Are we all on the same page? I'm just trying to find out I have a sequence. So this sequence has n terms. I want to make sure every single term is divisible by 19. Do you guys follow me? Yes or no? Can I have some feedbacks? Yes or no? The other students? Okay, perfect. All right. So this is more go to a sequence problem, right? You see, in our today's example, the AIME problem, the 10 to the power of ij, this is more like a sequence problem, right? And our Euclid problem is also a sequence problem. And this problem is also a sequence problem. You see, to convert a divisibility problem into a sequence problem is something kind of like a common practice we like to do, right? At least you shouldn't be so surprised to see a sequence problem. So now it looks like I have a sequence. So this sequence, you know what? This is like a 0, A1, A2, all the way to AN. Of course, I know A0 is divisible by 19, right? I know A1 is also divisible by 19. All the way, I want to prove AN is divisible by 19. Okay, so who can tell me? As long as you're dealing with a sequence-related problem, you are talking about this ends. Normally speaking, what is the common strategy we need to use in order to solve such a problem? What is the common strategy you need to use in order to solve such a problem? We're talking about a sequence-related proof. We're talking about some n-related stuff. Who can tell me? In your previous lectures, so on and so forth, Did you learn some technology? What is the common strategy to prove such kind of sequence-related n problem? Sequence and n related problem. I don't know if you guys know this or not. Do you guys heard about this? Some other math courses, for instance, have you been to some other math courses and you realize what are you going to do for that? Yes, I see Alex has an answer. Then what about the other students? This should be a conditional react. Yes, I see Hansen has the solution as well. I'm gonna ask maybe Hansen for this time. What are you gonna do?
I forget the name of it, but it's like you find out a sequence where n equals to 1 works, and then if n equals x works and n equals x plus 1 also works, then the whole thing works. Is that like mathematical induction? I forget the name.
Exactly. That's the famous mathematical induction method. This stands for the induction. Trust me, especially when you go to high-level math competition, this is extremely important. You're going to use the induction to get what you need. Very important. All right. So let me have a quick survey for most of our students. Do you know this induction method? Because this is outside the scope of our current lecture. We just happen to see such an interesting problem, and then we have to use that methodology. If you tell me you never heard about it, no problem. Because in our session 1, we're going to use a very good, like a very decent amount of paragraph talking about the mathematical induction method. This time, this is not our focus. We just want to, you know what? We just want to use it. Okay. If you do not understand what I'm talking about, totally no problem. This is outside the scope of our lecture. You can just take this as an kind of like a opportunity to expand your horizon. Okay, but it's not really compulsory. So mathematical induction method, you're going to go for basically 2 steps. Step 1, whenever n is equal to 0, you want to make sure the property holds. And then step 2, you want to hypothesize if n equals to k, the property holds. You want to prove n equals to k plus 1, the property also holds. This is the core business of doing the induction. Okay, like the reasoning behind that, I think, again, is outside the scope of our current lecture. I'm not going to expand too much, but at least this is kind of like a methodology. If you want to have, for the students who never heard about it before, maybe you can text me or you can talk to me offline. I'll be able to provide you some extra information. But I'm not going to use maybe half an hour explain why this is working. That's actually in our session 1 in the sequence and proving strategies. We're going to talk about it. This is a very important strategy, especially you're talking with the sequence related problems. All right, so let's try to use this. Let's have a look at it, how this one works. Step number 1, if n equals to 0, the property holds. N equals 0, that's our A0 equals to 12008. Of course, 19 is divisible by A0. Step 2, if or suppose n equals to k, the property holds, aka AK 1, 2, 0, 3. There are k3s, right? 19 is divisible by AK. So my goal is I want to show n equals to k plus 1 k plus 1 threes. I also want to have 19 equals to ak plus 1, right? As long as I can get this, my work is done. Well, the most challenging part is I know 19 is divisible by ak. How can I prove 19 is divisible by ak plus 1? I need to find out the relationship between ak and ak plus 1, and then hopefully I get what I need. Is that right? I have to use, this is what I suppose to be correct, right? I have to use it here in order to make sure it works. So the $1 million question is, how can I find out the relationship between ak and ak plus 1? Between ak and ak plus 1. AK is what? 1, 2, 0, 3, 3, 3, 0, 8. There are k threes, right? AK plus 1. K plus 1 threes. How can I find out the relationship between the two? Again, when you are getting lost, you have no idea how to do. Still remember what we taught you to do? What is the common strategy to get started? Still remember? What is the common strategy to get started? Still remember? You always want to try with some easy numbers, find out a pattern, and hopefully it works for the difficult numbers. Is it right? You see, our lecture is well designed. The same strategy, we're going to use different problems, try to help you guys understand the same strategy, right? We're not randomly pick up some question. Okay, that's it. No, all the questions are well designed. Try to make sure you can use the strategy a couple of times, and then you will be able to learn and know it. Okay, you try to, every single word we talk about in our lecture, there's a reasoning. You will be reuse them in the future, right? Exactly like our previous AIME problem. If you get lost, K or something get lost, why don't you try something easy? Why don't you? So you want to find out a relationship between two adjacent terms, right? Then what about A0? What about A1? A2? A0 is 1, 2, 0, 0, 8. A1 is 1, 2, 0, 3, 0, 8. A2 is 1, 2, 0, 3, 3, 0, 8. Okay. I want to find out the adjacent two terms relationship. A1 equals to what? A0, there's nothing to say. Is there a relationship between A1 and A0? Is there a relationship between A2 and A1? I'm going to ask maybe Wayne.
For every AK plus 1, the corresponding AK is, for every AK, the corresponding AK plus 1 is going to be 10 times it and plus a 2 to 8.
Is that right? So Wayne directly gave us the correct answer, but I'm going to maybe give two kind of like elaboration here. A1 actually equals to 10 times A0 plus 2 to 8. A2 equals to 10 plus A1 plus 2 to 8. You know what? If you keep writing another, like A3 is actually equals to 10 plus A2, 2 to 0. So all the way, AK plus 1 is 10 times AK plus 2 to 0. Like I said, you always want to start it with something easier, and then you get a pattern. Just try to use the pattern for something difficult. This is exactly the common strategy for all the problems. So that being said, my AK plus 1 will be equals to 10 times AK plus 2 to 0. Okay, 10 times AK plus 2 to 8, excuse me, 2 to 8. You wanted me to, this is AK plus 1, right? You wanted me to try if this one is divisible by 19 or not. First thing first, 10 times AK, you just have the assumption that AK is divisible by 19. So that part, check, divisible by 19. And this guy, 2 to 8. 2 to 8 actually equals to 19 times 12. So this guy is also divisible by 19. Again, using our famous A, N. So therefore, A is a combination X plus N, right? So automatically, my 19 will be divisible by AK plus 1, right? So therefore, you just finish the 2 steps for our mathematical induction method, right? So therefore, 19 is divisible by AK plus 1, and therefore, all my sequence A1, A0, A1, all the way to AN is going to be all divisible by 19. That's it. That's the mathematical induction method. If you're not so familiar about mathematical induction, it doesn't matter, but at least you understand our proving strategy. How to find out the patterns from easy terms. We start with something A1, A2, A3, and then make it more generic to AK. You see? All those problems I took from the American, the Canadian, and even the Ukrainian problems, they're all talking about the same thing. Using what? Factorization. Find out a pattern from easy ones to difficult ones, and then using the linear combination between 2 terms. So trust me, these are something so important for our entire divisibility, if not entire number theory. So this is what we're going to be talking about for our entire lectures. So like I said, you need to learn from the methodologies, not only for the 1 or 2 problems. There are millions of problems right there, right? You can never cover them all, but the strategies are limited. As long as you know one, you would be able to apply them to more problems, and hopefully you'll be able to do all the problems using the same strategy. All right, yeah, this is our first lecture. We actually do a little bit over time. Sorry about that. So next time we'll be able to make sure we stick to our original time. So basically, this is how we're going to do for our lecture number 1, divisibility. Are we all good? So in our next lecture, we're going to go to our second topic. Let's talk about the prime numbers and composite numbers. All right, I'll upload our homework to our Google Classroom, and you'll be able to have one week to basically do your assignment. So far, so good? For the students, if you have some question about what is the mathematical induction method, you've never heard about it, let me know. Talk to me offline. I'll be able to provide you some extra information. But again, this is not required for our current session. This is actually our session 1, sequence and proving strategies. All right, I hope you guys have a nice weekend, and I'll see you guys for the next week. All right, bye guys. Have a good one.
I have a quick question.
Yeah, sure.
Like, are you gonna post lessons on Google Classroom or something?
You can talk to me offline. I can provide you the information.
Okay, thank you.
Perfect. All right, so other questions? Or we can just cut it good. Perfect. I'll see you guys next time. Have a good one.
Bye, have a good night.
Bye.